Okay, in the name of God, we start the third session for our course. As you see in the previous sessions, we started our course and the topic was about the fundamental of machine learning. And we explain some phrases, some words in this field. For instance, supervised learning, unsupervised learning, reinforcement learning, validation, cross-validation, training, batch online system, offline learning system, and like this. And now, from this session, we want to start some algorithms in this field. And as you see here, our main topic is computational methods for data analysis. If you remember at the first session, we said something in it. We said time frequency analysis, image processing, linear algebra, and singular value decomposition, ICA, and blah blah blah. Okay. And as you see in this main topic, I mean computational methods for data analysis, we want to discuss about the time frequency analysis, and we want to know more about Fourier Transform and wavelets. As an engineering, you know the Fourier Transforms. At least you hear about it. You have heard about the Fourier Transforms. You know something about it. We want to explain more about the context in this field and see some examples for Fourier Transform. Okay? Then our way in this session is analyzes the time frequency, studying about the time frequency. And the reference of this PowerPoint, of this course, of this session is reference C. Reference C, I opened it, I uploaded this in the LMS. Reference C, part 3, computational methods for data analysis, and chapter 13, time frequency analysis. We are here. If you want to know more and to study the details, you can follow this chapter. Then part 3, chapter 30. Okay. And now we started. In engineering mathematics course, you saw Fourier series. You saw if we have a periodic function, if we have 2 pi periodic function, I mean if we have f(x) plus 2 pi is equal to f(x), we said that this f(x) is periodic with the period of 2 pi. Okay, and we improved in that course that we can represent this f(x), and if f(x) was real, we can represent it with a constant plus a series of sinus and cosine. Cosine and sinus. Okay? And if your attention to this equation, you see that this periodic function, cosine and sinus, has some coefficients. And we can calculate these coefficients A0, AN, and BN. Okay? For instance, A0 for this function is like this. Can calculate by this equation. Okay? Like this. And I again remind you that I'm writing with a mouse. Then if my handwriting is not so good, it is because of this. Okay. And then after that, we said that all periodic functions don't have period 2π. Maybe the period duration was 2L. I mean, instead of 2π, maybe we have 2L with a generic periodic duration. In this way, again, we have some real representation of Fourier series. Besides, we can represent Fourier series in complex version like this. For instance, we said that fx is equal to sigma, like this, Cn, exponential function, and the power of this is I and px alone, but the periodic is here. And the coefficient Cn can calculate it from this. We have some properties in this field. For example, if our fx was real, then Cn or C minus n is equal to C conjugated n. We can improve it. I don't know you see this before or not, but we can improve it. Besides, if we have fx real, or for example even, you know even function? You know even function? If you know, please type it. What is the even function? Nobody knows? Nobody. Okay, I explain. This function, I'm sure you know, but maybe you forgot it. This function, like this. This function is an even function. The symmetry of this function is related to the vertical line. And if you see f minus x is equal to fx, we call this function f even. Okay? In contrast to this function, we have f odd. F odd, the shape of f odd is like here. I write it here. the symmetry of odd function is related to the central points to 0. And if you remember, f minus x is equal to minus f(x). Then this function is odd, and this function is even. Okay? Okay. Anyway, if our function was real and even, and what is the real? Real means the function doesn't have imaginary part. All the things, all the measurements in this fx is real. Doesn't have any imaginary parts. Okay? And if our function was real and even, then our Fourier series coefficients is again real and even. Real and even, we can write like this. For even, we can write this. For real, we can say that the conjugate of Cn is equal to itself. And if our function was real and odd, okay, the Cn would be completely imaginary. The Cn is completely imaginary, purely imaginary, and also even odd. It means like this. Okay? Do you have any questions? No question? Okay. Okay. We know these things. I hope you to know these things. After that, we said that, okay, our functions aren't always periodic. We have some functions that they aren't periodic, for instance, like this. It is not periodic. And how can analyze this type of functions using Fourier analysis? Because of this type of function, we have Fourier Transform. Fourier Transform means that we transform a function from X environment, from time environment, okay, to another environment, to another space. And another space is Fourier space, is Fourier environment. If we call it fx, okay, f is dependent on x, and if we transform the function to the Fourier space, the function is related to omega, to frequency. And why we use Fourier Transform? What is the advantages of Fourier Transform? Because sometimes in image processing, in signal processing, the information of frequency is better presented in Fourier space. Okay, some information, then in summary, some information in Fourier space is better represented. Okay, then we use these for equations for transforming this function to the Fourier transform. And after that, some person who names Cooley and Touquet developed this commonly Fourier transform, and they introduced fast Fourier transform, and this type also has some advantages. We try to see the advantages in the next slide. But before it, we introduce the application, one application of fast Fourier transform. Please imagine it in a cylinder here, okay? This cylinder sends, for instance, electromagnetic waves and try to detect a target. For instance, try to detect this airplane. It sends electromagnetic to target, and the target reflects the waves. Also, the targets observe a few part of waves, and from the reflection of this target and receiving it, this object can understand the place of this target, or can understand this target, can track this target. But it is too ideal in the real world. We have clothes, we have trees. Okay, we have trees. We have other targets around it. We have some instruments in the space that they also may reflect the electromagnetic waves. Then the received waves here is not related only to this target. It is clearly that related to other things like this. Then we receive electromagnetic waves with noise here. Okay? And from this system, from this simple system, we can use or set other example. For example, stealth technology, or radar jamming system. Sometimes, attention to this. The above images. These objects the radar send waves, but the shape of target is specific, and the reflection waves doesn't go to the center. The target reflects waves to other directions, as you see here. Or maybe the materials of target was special. Then instead of reflection, the material observed all the waves. Then we cannot track the target in this way or in this way. Okay? And another thing in this field is a jamming system. For instance, you imagine this target and imagine this airplane was desired or our desired object. The radar sent waves, but another fake target, another fake airplane send waves to radar, and then in this way we confused what is the desired object, what is the main object here, one or two. How we can distinguish between one or two targets, target one or target. Then we called it parasite. Okay. Then in both system, in both example, we can use Fourier Transform. How? In the next slide you see it. You don't have any questions? Yes, surely. I uploaded it. Okay. Today I uploaded. Okay, another question. Yasmin Nazim said no sound, but I think it is okay. Maybe it is related to your internet. Okay. Please imagine we have a noise like this. We have a signal with white noise like this here. Okay. We want to distinguish and this noisy signal received in the by radar system. Okay. We want to extract the main signal without any noise. Then we want to filter the noise. If we use the Gaussian filter like this, with bandwidth, for example, 0.2 and centered on the and then if we use inverse Fourier transform, we achieve this pink signal. And if we compare this pink signal with our original signal, we see that the pink and blue is near to each other. It is not as same as but they are near to each other, and it is acceptable for us. And on the other hand, in the right figures, if we select our Gaussian filter with wrong parameters, for example, we again use this Gaussian filter, the bandwidth is 0.2, but it's centered at 15 frequency here. After filtration in the frequency domain, we have this, and then if we use Fourier Transform inverse, we have this blue signal. Okay, and it is clear that this blue is far from the origin. Then choosing the parameter of filtering in the Fourier Transform is so important. And another thing from this example, you can see that by filtering in the Fourier domain, we can remove the noise. Then one application of a Fourier Transform is denoising the signal. How? For example, like this example. Don't question? Any questions? Okay. Another thing for this application, for instance, if you have some signal in Fourier Transform, and we average the signal in Fourier domain. For example, in A, it is the one signal, B is the average of two signal in Fourier domain, C is the average of 5 signal, and D is the average of 100 signal in Fourier domain. It is clear that when we have a large number of signals and we average them, our result is better. Do you think why? It is related to the noise, the kind of and the type of noise. Because here the noise is white. The center of noise, the frequency of noise is 0. Then by averaging in frequency domain, we can remove the noise. It is another advantages or another application in this field. But in contrast to this example in the left, consider this figure, right upper. We have many signals in time and the shape of this. We have noise for each signal in time domain, and if we use Fourier Transform, we have this figure. You see in the Fourier Transform the location of noise missed. all the Fourier transform of these above signals has the same, you see, noise signal in Fourier domain. And we cannot distinguish between, for example, 1 and 2. If we use Fourier transform inverse, really only with this information we cannot relate 1 or 2 to this signal or this signal or another signal. This is the disadvantages of Fourier transform. The Fourier transform cannot distinguish the location of some frequency. Okay, and this is another application of fast Fourier transform. The above figure shows that the average in the time domain, and the lower one is the average of signals in a Fourier domain. It is clear that the averaging in Fourier is better than the time domain. In time domain, the information lost, the information missed. But in Fourier domain, in frequency domain, the noise, after averaging, the noise can be observable, can be detectable. Okay? The code of this and the explanation of these things is chapter 30. Completely, the codes step by step, explain and achieve this diagram that I explained to you. Okay? Okay. And in summary, we can say, for instance, consider this signal ST. It is in the time domain, and if we use Fourier transform, we have this diagram, this figure. Totally, for example, if I zoom on it, and zoom on it, if you consider this figure and attention to the changes, time changes. Time changes can be reflected by frequency. Time changes can be reflected by frequency. I mean, for example, imagine this signal and imagine this signal. Both of them in time. Finally, one student type something. Please let me read it. Okay. I explained it. Okay, consider these two signals. What do you think about the frequency? The frequency, we call the frequency of the above signal F1, the frequency of the lower signal F2. Which of them is higher, F1 or F2? Please type it. Please type your idea about the frequency of these two signals. The frequency of above signal or lower. Thanks. Mr. Ali Abdul Abbas Hussein Jamali, if I pronounce correctly, said that the second. Yeah, it is correct. Frequency means changes. I will answer you. Safa Abdul Jalil Tarwil, I will explain. Please wait. Okay. Then we have changes like this. Now the signal is lie on this pink. Besides, we have changes here. If we called it F1, F1 of these changes here in this part is greater, for instance, F2, we called it A, we called it B. F1 is higher than F2 in part B, because the changes of signal in A is higher the changes of signal in B. Okay? But if we use Fourier Transform, we only said that, okay, we have some frequency around 0 here. Maybe this is related to this pink. We have this frequency F1, maybe it is related here. I wanted to say that by using Fourier Transform, we can access only the amount of frequency. But we cannot say, okay, F1 in the first of the signal. We cannot say the location of F1. By Fourier Transform, we can access to the frequency context of the signal. Okay? Only we can access to the frequency signals. And then, this is disadvantages of Fourier Transform. And another question is that what is the Fourier Transform good for in the context of signal processing? If Fourier Transform has these disadvantages, then what is the benefit of using Fourier Transform? Why we use Fourier Transform? To answer this question, please consider two signals in left and right. As you see in right, we have some changes in signal. But these changes repeated. After duration time is repeated. Okay? And consider the left signal. We have some changes here. Then the changer is higher. Then again higher than the previous parts. Okay? The frequency content, the frequency information in the left changes during time. The frequency information changes during time. But in right, the frequency context, the frequency changes are stable during time and repeated again by again. Then, by our knowledge till now, we said that the Fourier transform is good for this type of signal, but it is not good for the left. Because for left, we only can say, okay, we have 15, 100, and 150 frequency. And we cannot say the location of it. And again, please consider the right Fourier transform of signal. Again, we see that, okay, 50, 100, and 150. These two Fourier transform are similar to each other. We call the right signals stationary signal. It means that signal with frequency content unchanged in time. Or another way, all frequency component exists at all times. But in the left we have non-stationary signal. Frequency changes in time. And ultimately the Fourier transform is superb for one thing, characterizing a stationary or periodic signal. Because they are unchanged during time. But it is not proper for non-stationary signal. Our bio system, if we have some biosignals, for example, the signals of heart, or human heart, we called it ECG. The electrical signal of head, we called it EEG. They are non-stationary signal. Then we need some other methods for this non-stationary, for analyzing of this non-stationary signal. Okay. If you don't have any question, we stop till slide 11, and the remain was for offline that I will record it and upload it in the LMS. And one student said that Muhammad Rashid asked many questions. No, this is related for advanced algorithm. But in DSP, I also teach DSP. In DSP, we have discrete Fourier transform. And discrete Fourier transform is a little different from this. The formulation, the concept is different. But for the introduction of Fourier transform, they are common for both of them, DSP and advanced algorithm. Oh, okay. It is good recommendation. Yes. He said that we uploaded the PDF before the session. Okay, why not? I will do it in the next session. And Safa Abdul Jalil will ask, will depend on the book or slides, both of them. The PowerPoint, the slides, is the abstract of book. Then you please first see the slides and see what is the important things, what is the important context, and then after that you can study in details by book. Okay. For instance, we review all of these and we abstracted, we shorted all these in only 10 slides. Okay? Okay. Any other questions? Okay. If you don't have any question, I will finish this session. Thanks for your attention. Thanks for your attending this class, and I hope to be fine and have good time.